Hello, dear audience. Professor Jacopo Ciambella from University di Roma La Sapienza, and he presents a seminar on damage detection in vibrating structural systems. And thank you for his presentation.
Thank you. First of all, thank you very much for being here. It's a pleasure to be in this marvelous city, and I want to thank Professor Tufeci for organizing my visit. Today I will, as Professor Tufeci said, I will talk about damage detection, because I thought it was a topic which could be of interest for the audience. I'm in the civil engineering department, and so we'll show you some examples of damage detection in civil structures, but I will, as you will see, this is very similar to mechanical engineering things. So we tested beams and plates on this kind of structure. First of all, let me say a few words about my university. You may have heard of Sapienza. Sapienza is the second university founded in Italy, 1303. I believe it's the largest in Europe. This is the number of students, so more than 100,000. So there are three main universities in Rome, public university, and then there are a few private universities. Sapienza is the largest. We are 4,000 staff members, okay? And of these numbers, of course, there are many faculties. The Faculty of Engineering, which is Faculty of Civil and Industrial Engineering, has almost 20,000 students. Okay, these are the numbers. We have different research centers. We are not in the main campus, I will show you, but we have research centers distributed all over the city. Okay? We often collaborate with NIS, which is the Nanoscience Center of Sapienza, which is in the main campus. Sapienza University, the Faculty of Engineering actually, is in the very center of the city. You may recognize the Colosseum. So the building is very old, probably like here, and for this reason sometimes can be very overcrowded. So our lab is in this part of the faculty here, and is attached to a cloister, a medieval cloister. So this is a cloister of there was an old convento of friars, and the faculty. In fact, this is the faculty is called also San Pietro in Vincoli, which means San Peter in chains, because it is thought that in this church here are the chains of St. Peter, the original chains. And it's very beautiful because there is the Mosè of Michelangelo, a very famous statue. So if you have a chance to visit, it's not only for the research, also for the surrounding areas, it's very good. I just want to mention something about my department, which is the Department of Structural and Geotechnical Engineering. We have different facilities. The things I will show you are mostly carried out in our lab. And with these machines, we have a shaking table, uniaxial shaking tables. The size of this is 2 meters by 2 meters. So you can test not very large, but quite large prototypes. We also have the frequency up to 100 Hertz. So this is the kind of frequency you expect from civil engineering structures, not more than 100 Hertz. Then we have testing machines, very similar to the one you have here, probably larger load cell, 40 kilonewtons, something like that. And then we have, for smaller scale prototype, we have shakers up to 2 kilohertz, where we tested normally smaller scale prototype. What we do, I decided to put these case studies. These are, because I didn't know what audience to expect. So if in case there were students, they may be interested in these case studies. These are a practical application we carried out recently. So we did what we do in the civil engineering department. We do static characterization of infrastructures, so mainly bridges, large bridges, not directly me. So we do essentially testing of materials and of the structures. You can see here there are some load put on this bridge. You may recognize this structure because it's a structure very similar to the bridge collapsed in Genoa last year, Polcevera bridges. We had a very tremendous, tragic episode last year in Genoa where the entire bridge collapses after a thunderstorm. This is the same made by Morandi, the same engineering. And we did static characterization here. We also do dynamic characterization, which is more similar to what you do in a mechanical engineering department. So what we do, we reconstruct the dynamic response of bridges by measuring accelerations. So we put on the bridges several sensors, 3-axial accelerations, and we try to measure the dynamic response. These bridges is was supposed to be one of the highest in Europe a few years when it was built in the 60s. It's called Viadotto Italia. It's in the south of Italy. Okay, and then we did some testing on these. We also test other type of structures. We work in collaboration. They have been building new underground lines in Rome for the past 15 years. It's been a very slow process because I think it's a similar situation. Every time they dig something, they found an ancient ruins, so they have to stop, remove the ruins and test again. So the underground line has been building for the past 15 years. Probably it's not finished yet, but we did some experiments on wave propagation. So because whilst they were doing the tunnel, they were concerned about the vibration entering the building, because in the building there were some computers, servers, which couldn't go offline. So we did measure the response and we tried to predict the type of acceleration expected during the drilling of the tunnel. Other type of tests we did on sound absorbing barriers for trains, but this is quite standard. Again, dynamic response with accelerometers. And of course, we are so close to the Colosseum, so we did some testing on the Colosseum. So dynamic reconstruction of the response of the Colosseum. But what I want to talk to you today is much more focused on damage detection. Okay? If you have a vibrating system and there is a damage, you want to be able to locate the damage, identify the intensity of the damage, and eventually predict the residual life of the structure. These are the three main objectives of a damage identification procedure. And as I said, these are the type of structure we are interested in. Bridges, where the crack can be localized. This is repaired bridges with external reinforcing composites here. The bridge can be also made of composite materials. This is a bridge deck in glass reinforced fiber. And when you use composite materials, you can the type of damage you expect is a bit different, because in civil structure you have very localized damage initially. So you have a crack propagating in a certain position, very localized. In composite, it's very easy to have delamination, so very diffuse cracking. And concerning to these two structures, what you can do to detect damage, the easiest way is to measure modal frequencies and to see how the eigenfrequency of the system changes with damage. And this will give you a clear indication of the presence of damage. You can use a minimum number of sensors to measure the eigenfrequency. You only need one accelerometer put in the right place of your structure. And if there is a damage, a significant damage, the frequency will change. But if you want to do something more, you can, for instance, look at modal displacement, so how the modal shapes changes with damage. And these all not only give you indication of the presence of damage, can give you also indication of the position of damage, which is also very important. I don't want to talk by eigenfrequency and modal displacement. I will focus on two techniques. I want to use modal curvatures rather than modal displacement, so the second derivative of modal shapes. And another technique we've been approaching very recently, in fact, we only show you preliminary results on a technique which is called empirical modal decomposition, which is using in between modal displacement and modal curvature, I should say. So motivation on the research, I think, are clear, but as I said before, why damage detection? In damage detection, we want to try to understand the presence of damage. There is a damage or there is no damage in the structure. We want to, at different level of abstraction, we want to locate the damage not only say if there is a damage, but where the damage is. We want to quantify the damage, so quantification, so how in terms of, for instance, of stiffness reduction, and also we want to estimate the residual life of the structure. This is what is normally called prognosis of the structure. This is very difficult normally, to estimate the residual life. You can deal with, in damage detection, with different quantities. You can do physical property, use physical properties, so how the damage affects mass, stiffness, and damping of the structure. You can use modal properties. The one I'm going to use in this presentation means that you can look at natural frequencies, mode shapes, or modal damping, or modal curvature also. And you can treat the structure as a black box. From the signal processing point of view, you can use Fourier transform or Hilbert transform, for instance. And there is no unifying approach for doing this. And I should say, in this presentation, I will start with number 2, and then I will show you something about quantification of damage. Talking about modal curvature. So modal curvature, as I said, is the second derivative of modal shapes. And because curvature is essentially a measure of deformation, we expect, if you consider a beam, this is a simply supported beam, okay? What you expect is that if there is a stiffness reduction in this position, the curvature underneath that sensors will be changed. So the difference in curvature will be localized around the damage. And the first observation is made about this fact were made by Pandy in a seminal paper in 1991, where they do numerical experiments and they compare modal displacement difference. When I say difference, I mean difference between the undamaged system and the damaged system. So in everything I will tell you, I'm always assuming that you can measure both the system at state 0, so that means that the undamaged system, and the system after the damage has occurred. So you have access to both these data. And so if you compare modal displacement, these are the first 5 modes difference, you see that there is no clear indication of where the damage is. So the damage is simulated around element 13 here, which means it's around here. And so if you compare the modal displacement before and after the damage, you don't see any clear indication of where the damage is. The things is different for modal curvature. If you compare modal curvature, so the first 5 modal curvature, you can see that there is a clear indication, at least for the lower modes, of the position of the damage, which was here. Things becomes a bit more complicated for higher modes, mode 5. These are numerical data, so there is no experimental error here, no simulated error. These are pictures taken from this paper. And so what when we start looking at this problem, we ask ourselves, so modal curvature can be used in damage detection in beam. That was the idea. So comparing modal curvature rather than modal displacement seemed a good idea according to that data. And so what we did, we studied the problem from the analytical point of view. So we used a perturbative solution of the Euler-Bernoulli equation. And then we find out, I will show you an analytical expression of the modal curvature difference. And the most important, we propose a filtering procedure. So what I mean for filtering procedure, so a procedure for which you can get the modal curvature difference, remove the unwanted information from the difference, and have a clear indication of the damage shape. So let me point out some notation here. For a damage, I will mean a stiffness reduction. EI is the bending stiffness of the beam. So, and is a function, in general, is a function of the x, which is the abscissa along the beam length here. And so you have EI 0 is the undamaged stiffness, and then it's reduced by a quantity which is supposed to be small. Epsilon is the damage intensity, which is small. Eta is this function here, which gives you the damage shape. Okay, so it can be whatever you want. So S0 is the center of this function, and B is the size, the width of the damage. Okay, you can modulate this. It's just an analytical representation of the damage. And so what we do when you do beam dynamics, you start with this equation here. The only difference, I will use an hash here to indicate the damaged quantities, and at 0 to indicate the undamaged quantities. So you start with the standard beam equation, the only difference with Euler-Bernoulli beam model. So the beam is slender, it's supposed to be slender. There is no shear effects in the beam, so it's quite standard. The only difference is that you have stiffness variation. So the stiffness along the beam is not constant anymore. And so you can do a perturbative solution of this equation. What do we mean perturbative solution? So you look to a solution of this form, a standard undamaged modes, I is the mode number, plus a perturbation of the order of epsilon. And the same thing for lambda, which are the eigenfrequencies of this system. And so if you plug this, so you substitute these two equations to expansion into the beam equation, you get the zero order equation. This is standard in perturbative system. So you get the equation of the undamaged system, plus a first order approximation, which is the first order correction to the equation. As expected, the structure of the differential equation of the first order is exactly the same as the zero order here. Plus, you have a forcing terms, which depends on the solution of the previous equation there, which is VI0. Okay? And eta I is nothing but the projection of the damage shape over the ith model curvature. That's why I put an I there. So if you do some calculation, you can work out the damage model shape. This is model shape. And you have this expression here at the first order. Okay? You do other calculation, which I will skip now. You can work out the modal displacement difference, I. So this is the difference of the ith modal displacement. So displacement of the undamaged modal displacement of the undamaged system minus the modal displacement of the damaged one, and so you end up with this closed form expression, where you have the difference in the eigenfrequencies here of the undamaged system, and this is a scalar product. So this is the projection of the function eta I over the W cap k, which is the modal curvature. And essentially what you want to reconstruct in a damage localization is eta I, because eta I contains the damage shape. This is what you are interested in, the damage shape in this problem. So this is the direct problem. And then you can do the same for modal curvature difference. You have the second derivative of the modal shape. So the expression is similar here. The only difference is that rather than have modal shape here, you have modal curvature. W is the modal curvature. After some manipulation, you can have an expression of the modal curvature here, where it appears eta I, again, which contains the damage shapes, plus different terms. And this is interesting because this is, I want you to analyze this equation more in details. There are three terms here. A red term, which is eta I, it exactly contains the damage shape. As I said, is the shape of the damage multiplied by the ith modal curvature. And then there are other terms which needs to be taken into account when from the experiment. From the experimental data, you measure this. You measure the modal curvature difference. And you want to reconstruct the red term. That means that you want to filter out the green and the blue term in this way. So the green term is the ith modal curvature. The blue term contains contribution from the other modal curvature. This is a sum over all the modes, k not equal to I, and so you have all modal curvature here. So you can work out eta I here and have this expression here, which is essentially tells you that if you measure delta I modal curvature difference, you have to remove this term to have a clear indication of the damage. Okay? And the problem is the following. You can have, in measuring this, okay, these terms here, the green and the blue, can get very big. So can either cancel out the red one. I will show you some example of this. Okay, this is in terms of analytical solution, everything here is not, we are not talking a specific system. We are talking about a beam. I didn't put any boundary conditions. I didn't solve the boundary volume problem. Now, if I focus on simply supported beam, the advantage is that for simply supported beam, you have a closed form expression for the model shapes and model frequencies. So essentially, I can compute all these terms in closed form here. I know how the model curvatures are. I know the model frequencies, and so I can substitute this expression into this equation and obtain this expression for the model curvature difference. And so you have different terms. Again, you are interested in this eta, but you see there are different coefficients here. And when these coefficients becomes very large, this coefficient has a maximum in 1, this function eta. If this coefficient becomes larger than 1, you are in trouble, because in your experiments then you won't see any damaged shape. This function here can be well cancelled by the experimental error. So you want to be sure that those two coefficients stay small. And this is what is plotted here. This is the plot of alpha 1, for instance, in terms of two damage parameters, which is B, the thickness of the damage, and the damage position. Okay? And for instance, this alpha 1, which is the coefficient of the first model curvature difference, can be up to 0.67, so it can be comparable with this eta. And the same thing for alpha 3, alpha 2, and these other coefficients, so it can be very large. And what happens is the following thing. I plot here what I call worst case scenarios. Let us imagine that you have a very large damage. We are not talking about intensity. The intensity is small. Let us imagine that you have a beam with a delamination. And this delamination spans the entire beam length. This is the damage shape here. What you want to compute the model curvature difference. And when you look at the model curvature difference for mode 1, for instance, you end up having this. 3 lobes. So you don't have any clear indication, because this is the case where those coefficients are very large. And then for mode 2, in these other damage case scenarios, you see you are here. The damage span the half of the beam length, and then you have all these lobes in the damage model curvature difference. So again, looking at model curvature themselves, you don't have any indication of the position of the damage. And then this is another case. So you need to take into account this factor, and by properly filtering the model curvature. Okay? And how filtering them, you can see from this equation here. So you need to remove this quantity here. And so I will show you an application, not on beam, but on a parabolic arch. Okay? I show you the beam equation, but the same calculation can be carried out for a parabolic arch. Okay? You can then end up having a very similar filtering procedure. So you can have the model curvature difference, and you know exactly what terms you have to filter out, remove from the model curvature difference. So we did experiments on a parabolic arch. So 1 meter was the arch span with accelerometers, 7 accelerometers. And what we did, we measured the model response by simulating a damage. How? We put a small crack here. The width was 2 millimeters, so very thin, and with different height. We tested different height. So the height is here. The ratio, this is the ratio between the damaged height and the undamaged height of the arch, which was 8 millimeters. Okay? So we tested different damage case. Damage 1, which means 12% of the height of the intact beam, up to 50%. So we remove half of the height from here. And these are the frequency variation for the first 4 modes. Okay? So as you can see, the undamaged had a frequency of 50.4 hertz, and then because of the damage, the frequency decreased as expected. So you are reducing the stiffness of the structure, and so all the frequencies of the mode shapes decrease. And the mass reduction is not significant in this problem, okay, because the thickness of the damage is very thin. So the quantity of material we removed is very small. And so what we did was to compute modal curvature difference with that filtering procedure. So these are the filtered modal curvature difference. And as you can see from the modal curvature difference from this problem, the damage was here, damage 1. The modal curvature difference gives you a clear indication of the position of the damage. Okay? For damage 1, damage 2. And so this indication becomes clearer, of course, when you increase the damage intensity from D1 to D4. So the difference between these is that the height of the damage has been increased. This function here is a function which I call BS. It's essentially an interpolation of the damage shape, if you want. And why I put this function BS? Because at this stage, we only know where the damage is, pretty much. So we know that it's located in this area here, only by looking at the modal curvature difference. What happens if you want to estimate the damage intensity, so the stiffness reduction? What you can do an inverse problem. Okay? You can do a model of your structure and define an objective function. And this is the objective function I put here. So we have an objective function which is based on the modal frequency difference, modal displacement difference, plus a term which depends on that pre-localization. Essentially, we use the information of the modal curvature difference directly into the objective function, and we compare the experimental variation of the modal frequency with the model. Okay, these are the results of a finite element simulation. K is the we simulate. I must say that in this problem here, we did a finite element model where we simulate the damage with a spring here between these two sections of the beam of the parabolic arch, between this section and this section. There was a beam whose intensity was K. The objective of the inverse problem was to identify K and eventually the position of the damage. Okay? And so this is what we have done. This is the function G in different case. The function G only with, you can't read very well, but this is the thin one is GF. GF means an objective function where you compare only this first term here, modal frequency. Okay? If you look only at the variation of the modal frequency, you have an indetermination. The problem is indeterminate because it's symmetric. So you can't distinguish damage which are on the left side on the right side. And you can see this by the fact that this objective function is symmetric with respect to 0.5. Okay? So it means that you compare modal frequency, you cannot decide modal frequency only, you cannot decide if the damage is here or here, because of the effect on the modal frequency are exactly the same. So you have to add more terms in your objective function. So what we did, we add the modal displacement difference, and this is the thick curve here. And by adding modal displacement difference, you remove this indeterminacy. Because in the modal displacement, you have a bit of information where the damage is. Okay? And in fact, the objective function, so it's not symmetric anymore. And it tells you, I should say quite clearly, that the damage is here. The things get a bit better if you add this term here, which is an information coming from the modal curvature difference. So a sort of pre-localization. The function B is this function I showed you before, is this function here. Okay, and so as you can see, if you add B, the problem gets much easier to solve. There is a clear indication of the position of the damage, so the objective function has only one minimum, and also you can estimate the stiffness of the beam. And these are the results for the different case I examined before. So D1 is the weakest damage, okay? And these are the results with the functional, with only the frequency and the modal curvature, the frequency, the modal shape, and the modal curvature. Okay? You can estimate 20% of error on the damage intensity. This is the error. The position was estimated quite well, I should say. So 0% error, no more than 2%. But the intensity was not very well captured, you see. If you add the model shapes, things get better, and the error in the inverse problem is below 3%. Okay, quite accurate. And the position of the damage was, the error was, in any case, below the 2%. So again, this is the functional, is the thick black functional here, okay, minimizing that functional here. So you have a good estimate of the stiffness, reduce stiffness of the system, and also the damage position. And then we did test in the real case scenarios, but I want for different scenarios, but I want to talk to you about another technique which I've been recently using, which is called empirical model decomposition, okay? Not model curvature. So we did testing in this small frame prototype for 4 floors, and we did have stiffness reduction in different places, 2nd floor and also 3rd floor here. This technique, empirical model decomposition, was proposed relatively recently in 1998, 20 years ago actually, and is a technique which uses combined information from time domain and the frequency domain. I will tell you a bit more about empirical model decomposition here. So what you have, imagine to have a signal like this, okay? So it's a 2-component signal. You have 2 tones, so the sum of a sinus at frequency f1 and a cosinus at frequency f2. The resulting signal is this one, okay? It's the blue curve. Now, the empirical model decomposition is based on this, what I call intrinsic mode function, and how the intrinsic mode function for this signal here are plotted here. So this is the intrinsic mode function 1, intrinsic mode function 2, and so on. And I will tell you how these are constructed. These are not the proper mode, the mode shape of this, because the mode shape are, in this case, are simply 2. It's the first one, which is sinus f1 and so, and the second one, which is cosinus f2. Here we have more intrinsic mode function, and these things are constructed with algorithmically in this way. So you start with the initial signal, which is the blue one. You take the envelope of the maximum and the envelope of the minimum, and you make the mean of these 2 signals, the green and the red. And you get the purple signal. And then this is iteration 0. And then you pass to another iteration where you compute the difference between the blue and the purple signal, and you start again this procedure. When this purple signal becomes lower than a certain threshold, you stop. And the resulting signal, which is the blue one, will be your what is called intrinsic mode function 1. Okay? And I will show you the property. So it's quite algorithmically. It's data-driven. So it doesn't come out from a mechanical model of the system. It's purely data-driven. But it has this intrinsic mode function has some nice properties. Nice properties because they are very similar properties as the mode themselves. So the mode are in the frequency domain. So they are each mode is associated only to a 1 frequency. Intrinsic mode can be associated to more than 1 frequency. So this intrinsic mode function can be associated, I will show you to do 2 frequency or more, but you can do the same analysis you can do with the standard mode. So you can do, you have an indirect, the same analysis means that you can do time domain analysis of the intrinsic mode, so you can estimate the logarithmic decrement to estimate the damping of the structure. You can have the study them in the frequency domain, and by estimating, for instance, the 0 crossing here in the time domain, you can estimate the frequency of the mode. You can do peaking, all the standard things. So they have the same property, but with more than 1 frequency. Let me skip this. I will go to an example here. So this is numerical. It's not related to the example I showed you before. It's a two-story building simulated with a certain stiffness here, K1, certain stiffness K2 of these other beams, and a certain mass of the two floors. Okay? We look at the mode shape. Here I plotted the first two mode shape, mode 1 and mode 2. These are the damping of this problem, and these are the modal participation factor here. First frequency, second frequency. Now, let's assume that we do an experiment, okay, on this system. There was a model, so I want to do an experiment here. So I just put, I impose a velocity of this point. With this is an initial condition, and I look at the free vibrations of the system. By measuring the response, I imagine to measure the acceleration on the second floor and on the first floor. Okay. These are the results of the identification with the technique, but rather than looking at the number themselves, so the results were pretty good. I use empirical mode decomposition here in frequency and in time, but I want to show you this graph here. In blue, so under the red curve you can't see very well, but those are the mode shape, the standard mode shape. So these are the free oscillation associated with mode 2, okay, with a certain frequency here. And then above that you have the intrinsic mode 1, which do this strange thing. It starts to decreasing, and then increase again here. Okay? What we expect from the free response, free oscillation of mode 2 is to logarithmically decrease, no increase anymore. And the opposite happens, for instance, if you look at the intrinsic mode 2 compared to the first mode shape, so the oscillation associated with the first mode. You see that the first mode decrease, and then the intrinsic mode 2 has this strange behavior. It goes like mode 1, and then at a certain point immediately decrease. Okay, and so the same thing happens for intrinsic mode 2 compared to the mode. And why so? I will explain that. This is a different example with 4 floors. Okay, we did exactly the same, and we impose a velocity here, and we record the acceleration on the 4th floor. Okay? And these are the results. So similar problem. These are the actual response here of the system with this initial data. And this is the intrinsic mode 1. You see that the intrinsic mode 1 has this strange envelope. Okay? I recall you that the standard mode would logarithmically decrease. And so there are, in this intrinsic mode, there are clear 2 regions, okay? The gray region and this region here. If you zoom here, you see these kind of things. So the intrinsic mode is the blue curve. And then here I plot also the mode 1 and mode 2. Sorry, mode 3 and mode 4. Mode 3 is the red curve, and the mode 4 is the green curve. So you can see in this first part, the intrinsic mode is very similar to the red curve. So it's going like mode 2. But then if you zoom in this other part, okay, what you see that is the intrinsic mode, which is again the blue curve, is initially going like mode 2, sorry, which is the purple curve, and then it goes like the Q3, the mode 3. So essentially the message is that the intrinsic mode contains information for all the 4 modes we have seen here. Okay, either in terms of frequency and in terms of damping. And you can see that in this picture, in this graph, where I compute either the wavelet transform of this signal here and also the Hilbert transform. So the wavelet transform essentially gives you information on how the frequency, the proper frequency of this signal, change with time. So 10 seconds, and you can see that you have information on different frequencies. Initially, they frequency content around 10 Hz is quite significant, and then the information moves to the other mode, which is 6 Hz. And this is clear from this Hilbert transform. So this is the main frequency of the signal initially is 10 Hz, and then it jumps to 6 Hz, which is the second mode. So with the intrinsic mode, essentially by manipulating only one intrinsic mode, you get information of two different modes. These are numerical results. So no error, no experimental error, nothing. We did test actually the real structure, as I said before. The real structure was this 4-story steel frame with damage. In this case, the damage was at the level of the last floor here, and was a stiffness reduction into column. We introduced a small stiffness reduction. We did test with the instrumented hammer, and we record the acceleration. And these are the results. For instance, we have the undamaged system, okay, acceleration of the undamaged system, and the damaged one. And I compute here the intrinsic mode 1, intrinsic mode function 1, and the intrinsic mode function 4, for instance. And this can be affected by noise. So our intent was to estimate how the noise affects these two functions, these two intrinsic modes. And the problem is the following. So with standard mode, you have a clear indication that mode 1 corresponds to the first frequency. Okay? So you have a clear indication of the mode number. Intrinsic mode is not anymore the same, because as we have seen before, the intrinsic mode 1 had the information on the second eigenfrequency and the third eigenfrequency. So the mode number is not anymore directly related to the frequency of the system. So what we did was try to estimate what mode number were the most significant. And so I plotted here the energy associated to each of these intrinsic modes. Okay, this is a plot of the energy, the power of each mode. For the first 15 intrinsic mode, and you can see that there are some modes with more energetic contents. Okay, see, either for the undamaged and for the damaged system. Okay, so we concentrate the analysis on those modal indices. Here you have the modal indices, so the indices of the intrinsic mode. And so we concentrate the analysis on 6 different modes, which I rescaled here, the one which had the more energetic content. So we had to find a way to establish which one was more significant for our procedure. And how we did that, we look simply at the energy in each mode. So we pick up the modes with the greatest energy. And so these are the results. So we select the energy by using this energetic criterion here. P is the power associated with the damaged intrinsic mode function and the undamaged intrinsic mode function. And so we look at the difference in power. These are very preliminary results, so I don't have much more than this. And by looking at those 6 intrinsic modes I showed you before, and by using a standard identification procedure, we got these results here. So this is what we expect is that to see that the intrinsic mode difference, so the difference between the intrinsic mode of the damaged and damaged system, to be concentrated around the damage. Okay? Like we expect the same for modal shapes or modal curvature. I mean, it's not, at this stage I can see that this is a clear indication because this is the intrinsic mode difference for intrinsic mode 2. We have a peak here in correspondence of the 4th floor. I recall you that the damage is around here, between the 3rd and the 4th floor. So we were expecting to see in this difference a maximum around here and here. So there is a maximum for those two modes, but it's not very relevant compared to the other. Okay? And this is by simply comparing the intrinsic mode 2 for the damaged and damaged system without any filtering procedure. Okay? What we try to do now is to apply a filtering procedure to this mode to obtain a better indication of the damaged position. Okay? And the other things, by using, again, this selection criteria. Okay? This is the selection criteria we use, looking at the intrinsic mode function with the highest energy content. So other research topics. This is also something I wanted to mention, because this is something which I've been working on directly, but there are colleagues in my department working also on other fields. Nonlinear dynamics for vibration dampings. This is something I also been looking at recently for magnetorological system, okay, damping with magnetorological system. And so they study damping of large oscillation, nonlinear oscillation of this kind of system, essentially to extract energy, okay, for the purpose of energy harvesting. And then they also studied the coupled electromechanical system, okay, where the mechanical system is coupled with, for instance, with external magnetic field, okay, and how this coupling affects, for instance, the current into a solenoid. These are the reference. And personally, so it's exactly this is the same problem. So energy harvesting, okay, how to optimally tune. What they did is to try to understand how to optimally tune energy harvesters to extract energy from the system in case of large oscillations, because normally what is carried out is in small oscillations. So these energy harvesters are tuned within one frequency, and so they are optimally tuned around one frequency of the system. If you use nonlinear dynamics, you can try to enlarge the scope and make an harvester which is optimally tuned over a broader frequency range, which would be of interest. But I'm not personally doing this. This is the type of system they use. So they use an oscillating standard vibrating mechanical part, or coupled with an electromagnet. Okay? And they study the coupling between the currents in the electromagnets and the mechanical oscillation. And then something which I've been also working on recently is the magnetorological elastomers. Okay, so these are elastomers where you have fiber dispersed in it, meaning that these fibers are magnetically active. So you have a very soft matrix which can be actuated externally by a magnetic field. And so we studied different type of configuration where these are actual experiments. This is a small flap, so it's a small beam in cantilever configuration, and according to the fiber direction, you can either get bending or twisting of the system. Okay, and so this was quasi-statically done. Now we are looking at the dynamics of the system. And so here are some reference for the part of the vibrating system, and I'm happy to take any questions if you have any. 36.
Yeah, might not even be relevant or so, but I just wanted to ask, just curious.
Yeah.
In the second chart, is there a initial value at point 0, right?
This pack here, you mean? Yeah, I think so, because it's the...
It wasn't that clear
because the initial acceleration here.
Okay.
So I recall you, this is the intrinsic mode. It's essentially that algorithmic procedure I described before, taking the maximum of the signal and the minimum of the signal in making the average of them, iterating this procedure.
Requires an initial value then?
Yes. Okay. Yes. Okay. Thank you very much.